1.3 Trigonometric Functions. The outline of this video is as follows. We will begin our discussion with the fundamentals of angle measurement, learning how to work with both radians and degrees. From there, we will define the 6 basic trigonometric functions, including sine, cosine, and tangent, using the unit circle as our guide. Next, we will examine the repeating nature, or periodicity, of these functions, and visualize their behavior by studying their graphs. We will then cover some important trigonometric identities, specifically the double angle and half angle formulas, which are essential for simplifying expressions. After that, we will explore the law of cosines, a powerful tool for solving for sides and angles in any triangle. We will conclude by learning how to apply transformations to these graphs, allowing us to shift, stretch, and compress the basic trigonometric curves to model new situations. To prepare for calculus, we will measure angles using radians, a unit that directly relates an angle to a physical length. A radian is defined by a simple ratio. The measure of a central angle, which we will call theta, is the length of the arc it subtends, s, divided by the circle's radius, r. This means theta equals s over r. Rearranging this gives us a powerful formula, s equals r times theta, which tells us that the arc length is just the radius multiplied by the angle in radians. This direct relationship is incredibly useful. For a concrete example, consider a full circle. You know this is 360 degrees. The arc length is the entire circumference, 2 pi r. So the angle in radians is 2 pi r divided by r, which is simply 2 pi. The essential relationship to remember is that pi radians is exactly equal to 180 degrees. To analyze angles universally, we need a consistent framework, which we call standard position. An angle is in standard position when its vertex is at the origin and its initial ray, or starting side, lies along the positive x-axis. From there, the direction of rotation determines the angle's sign. A counterclockwise rotation creates a positive angle, while a clockwise rotation creates a negative one. For example, a positive 90-degree angle points straight up the y-axis, but a negative 90-degree angle points straight down. It is also important to know that angles are not confined to a single rotation. We can continue rotating past 2 pi radians, or 360 degrees, in either direction to represent any angle size. Placing angles in standard position provides the essential reference system we need to define their trigonometric functions. We can now define the 6 basic trigonometric functions for any angle by using a point on a circle in the coordinate plane, which greatly expands their usefulness beyond simple triangles. Imagine an angle theta in standard position, where its terminal ray intersects a circle of radius r at a point with coordinates x and y. The two most fundamental functions are defined as simple ratios. The sine of theta is y divided by r, and the cosine of theta is x divided by r. The tangent is then the ratio of y to x. The other 3 functions are simply the reciprocals of these first 3. Cosecant is r over y, secant is r over x, and cotangent is x over y. This setup perfectly extends right triangle trigonometry, because for an angle in the first quadrant, y is the opposite side, x is the adjacent side, and r is the hypotenuse. Remember that all 6 trigonometric functions are just the 6 possible ratios formed by the 3 values x, y, and r. Now that we have defined the 6 trigonometric functions, we can see how they are all related to each other through simple identities. First, the quotient identities show us that the tangent of an angle theta is simply the ratio of sine of theta over cosine of theta, and cotangent is the reverse, cosine over sine. Next, The reciprocal identities show that cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. A crucial consequence of these ratio definitions is that some functions have domain restrictions. For example, since both tangents and secant involve dividing by cosine, they are undefined whenever the cosine of the angle is 0. This occurs at angles like plus or minus pi over 2, where the x-coordinate on the unit circle is 0. The key idea is that you can derive all the properties of the other 4 functions directly from sine and cosine. We can find the exact trigonometric values for some of the most common angles by looking at the geometry of 2 special right triangles. First, consider an isosceles right triangle with angles of 45, 45, and 90 degrees. If we set the 2 legs to have a length of 1, its hypotenuse must be the square root of 2. This simple triangle shows us that the sine of pi over 4 radians is 1 over the square root of 2. The second key triangle is the 30609O triangle, which gives us the values for both pi over 6 and pi over 3 radians. Its sides are in the ratio 1, the square root of 3, and 2, where the shortest side is opposite the smallest angles. For example, from this triangle we can see that the cosine of pi over 3 is 1/2. By remembering these 2 triangles, you can derive the exact trigonometric values for many fundamental angles without a calculator. To easily remember where the trigonometric functions are positive or negative, we use a helpful mnemonic called the CAST rule. This rule assigns a letter to each quadrant, reminding us which functions are positive there as we move counterclockwise from the x-axis. In quadrant 1, the letter A tells us that all functions are positive. In quadrant 2, the letter S means that secant and its reciprocal, cosecant, are positive. Continuing to quadrant 3, the letter T means that tangent and its reciprocal, cotangent, are positive. Finally, in quadrant 4, the letter C tells us that cosine and its reciprocal, secant, are positive. For example, an angle of 2 pi over 3 is in the second quadrant, so its sine value is positive, but its cosine and tangent values are negative. The CAST rule is simply a quick check for the sign of any trigonometric function based on its angle's quadrant. The repeating, wave-like nature of trigonometric functions is formally known as periodicity, a property that is crucial for understanding their behavior. A function is called periodic if its output values repeat over a regular, fixed interval. More precisely, we say a function f of x is periodic if there is a positive number p, called the period, such that f of the quantity x plus p equals f of x for all values of x. For example, the values for sine and cosine repeat every time we complete a full revolution of 2 pi radians on the unit circle. It is important to remember that the period is the smallest positive value for which this repetition occurs. This gives us 2 groups to remember. The tangent and cotangent functions have a period of pi, while sine, cosine, secant, and cosecant all have a period of 2 pi. Let us now visualize the 2 most fundamental periodic functions, sine and cosine, whose wave-like graphs are essential for modeling oscillations. The sine graph begins at the origin, rises to a peak at 1, falls back through 0 to a minimum of -1, and then repeats this pattern every 2 pi units. Its domain is all real numbers, while its range is restricted to the closed interval from -1 to 1. You can see its rotational symmetry about the origin, which confirms that sine is an odd function. The cosine graph has the same wave shape but is shifted, starting at its peak value of 1 when x is 0. It shares the exact same domain, range, and period as the sine function, but it is an even function, which is clear from its mirror symmetry across the y-axis. The easiest way to distinguish them is that the sine graph passes through the origin, while the cosine graph has its peak on the y-axis. Now let us look at the tangent and secant functions, which have vertical asymptotes where they are undefined. The tangent function is the ratio of sine over cosine, so it is undefined whenever cosine of x is 0. This happens at odd multiples of pi over 2, creating vertical lines the graph cannot cross. Because of this, its range includes all real numbers, and its pattern repeats every pi radians. Tangent is also an odd function, meaning it has origin symmetry. The secant function, which is 1 over cosine of x, shares the same domain and asymptotes as tangents. Since it is the reciprocal of a value between -1 and 1, its range is everything outside that interval, values greater than or equal to 1 or less than or equal to -1. Its period is 2 pi, just like cosine, and it is an even function with y-axis symmetry. The key idea is that the properties of both functions are directly determined by the cosine function. Now I will show you how the simple Pythagorean theorem leads to the most fundamental identity in all of trigonometry. We begin with the equation for a unit circle, which is x squared plus y squared equals 1. Because we define the x-coordinate as the cosine of an angle theta and the y-coordinate as the sine of theta, we can substitute these directly into the circle's equation. This gives us the main identity: cosine squared of theta plus sine squared of theta equals 1. From this single powerful rule, we can derive two others just by dividing. If we divide the entire identity by cosine squared of theta, we get 1 plus tangent squared of theta equals secant squared of theta. Similarly, dividing by sine squared of theta gives us cotangent squared of theta plus 1 equals cosecant squared of theta. These three identities are essential tools for simplifying trigonometric expressions. Let us explore the addition and subtraction formulas, which are essential tools for finding the trigonometric values of angles that are sums or differences of other angles. A common mistake is to assume that the cosine of a plus b is simply cosine a plus cosine b, but that is incorrect. The actual formula for the cosine of the quantity a plus b is cosine a times cosine b minus sine a times sine b. Notice that when we add the angles inside the cosine, we subtract the products on the outside. The formula for the cosine of a minus b is similar, but the sign flips to a plus. The sign formulas mix the terms. Sine of the quantity a plus b is sine a times cosine b plus cosine a times sine b, and its subtraction counterpart follows the same pattern with a minus sign. For example, we can now find the exact value of sine of 75 degrees by calculating it as the sine of the quantity 45 degrees plus 30 degrees. These identities allow us to expand our knowledge of exact trigonometric values beyond just the basic angles. Let us see how we can use the addition formulas to derive another important set of identities for an angle and its double or half. If we take the addition formulas for sine and cosine and set both angles A and B to be equal to theta, we get the double angle formulas. The sine of 2 theta becomes 2 times sine of theta times cosine of theta. Similarly, the cosine of 2 theta becomes cosine squared of theta minus sine squared of theta. Now if we take that identity for cosine of 2 theta and algebraically rearrange it, we can solve for cosine squared of theta and sine squared of theta. This gives us the half-angle formulas, which express these squared terms using only cosine of 2 theta. For example, these are extremely helpful in integral calculus for rewriting expressions that are hard to integrate. The main thing to remember is that these formulas give us a direct way to relate the trig functions of an angle to the trig functions of twice that angle. Here we have a powerful tool called the law of cosines, which is essential because it relates the sides and angles of any triangle, not just right triangles. The law states that for a triangle with sides A, B, and C, the square of side C is equal to a squared plus B squared minus the quantity 2 times a times b times the cosine of the angle theta. But it is crucial to remember that the angle theta is the one directly opposite side AEC. You can think of this as a generalization of the Pythagorean theorem. For instance, if your triangle is a right triangle, then theta is 90 degrees, or pi over 2 radians. The cosine of that angle is 0, which makes the entire last term of the formula vanish, leaving us with c squared equals a squared plus b squared. The law of cosines simply extends this familiar relationship to work for any triangle you might encounter. I will now introduce two special inequalities that are fundamental for proving important limits in calculus. These relationships come from a simple geometric idea on the unit circle, where the length of an arc is always greater than or equal to the straight line connecting its endpoints. Since the arc length for an angle theta is just the absolute value of theta in radians, this means the absolute value of sine theta must be less than or equal to the absolute value of theta. For example, for a small angle like 0.1 radians, the sine of that angle is a number just slightly less than 0.1. A similar argument gives us the second inequality, which shows that 1 minus cosine theta is also bounded by the absolute value of theta. It is crucial to remember that these relationships are only valid when theta is measured in radians. The key takeaway is that these inequalities tightly bound the sine and cosine functions near zero, which is exactly what we need for calculus. We can create any repeating, wave-like curve by applying standard transformations to the basic sine function. This gives us the general sine function, or sinusoid, which is described by the formula f of x equals a times the sine of the quantity 2 pi over b times the quantity x minus c, all plus d. Each of these four parameters precisely controls a specific transformation of the graph. The absolute value of the parameter a determines the amplitude, which is the vertical stretch of the wave. The absolute value of the parameter b sets the period, or the horizontal length, of one complete cycle. The parameter c creates a horizontal shift, also called a phase shift, moving the wave left or right. Finally, the parameter d produces a vertical shift, moving the entire graph up or down. This single formula allows us to model many real-world cycles, like the voltage of an alternating current. The key takeaway is that these four parameters give us complete control to build any sinusoidal wave. Let us bring together the key ideas of trigonometry that are essential for calculus. We began with radian measure, which defines an angle as the ratio of arc length to the radius, providing a natural scale for these functions. This leads to defining the 6 trigonometric functions as ratios of coordinates on a circle, which is a powerful generalization of right triangle geometry. A direct consequence of this circular definition is their periodic nature. Sine, cosine, secant, and cosecant repeat every 2 pi radians, while tangents and cotangent repeat every pi radians. To work with these functions, we rely on key identities like the Pythagorean and angle addition formulas. Finally, a major application is the law of cosines, which states that c squared equals a squared plus b squared minus 2ab times the cosine of theta, allowing us to analyze any triangle. Mastering these concepts is fundamental for your success in calculus. A powerful application of the addition formulas is finding exact trigonometric values for angles that are not standard but can be built from angles we do know. The sine addition formula, for instance, tells us that sine of the quantity a plus b equals sine of a times cosine of b plus cosine of a times sine of b. To find the exact value for sine of 7 pi over 12, we first express the angle as a sum of two familiar ones, such as pi over 4 plus pi over 3. We then substitute these into the addition formula, using the known sine and cosine values for our two familiar angles to compute the result. It is important to remember that you cannot distribute the function, Sine of A plus B is not equal to sine A plus sine B. By using these identities, we can extend our knowledge of the unit circle to calculate exact values for a much wider range of angles.